first, user has to create an account from here. So after creating an account from here, user can sign in from here. I have already created an account, so I'm going to sign in. Yeah, so after signing, I should be redirected to this page, and here I can say get started. Here my documents will be loaded in no time. Since I'm using slower connection, it's taking some time, but in an ideal case, it should not take me so long. So I can create new document. So after creating this document, I will be directed to the editing page, so I can share it with someone who is already registered with the service from here. So now I can log in as that user and should be able to see that document. So see, I can see this the document here. So for a better view, I'll do this. So when one user is editing, other also can see the changes happening in real time. So this is what everything is intended, and it can, since this is a markup kind of markup, so they can uh, add uh, they can add styling as well. So like this. This is in real time collaborative document. So what happens is that each client connects through WebSocket to the backend, and backend has operations. I will show it through sockets, and I can send some content from here. So if I want to add something, so the version number should be the same. Right now it's 69, so I can send the version. So I think I send the version, and this time should be updated, and this operation came here, and the socket updated. I can do the same for both sides as well. So that's what basically happening here.
Hello, my name is Pasanabe Sekara, and for this assignment, I will be presenting our project Real-Time Collaborative Document Editor, designed and built using modern cloud-native principles. We choose this project because it's a complex, real-world system that provides an excellent opportunity to demonstrate all the core requirements of the assignment, from scalability and high availability to advanced communication methods and security. Before diving into the technical details, let's start a live demonstration of the core features. Here on the right, I have three terminals. That bottom one is my control terminal, where I will act as the user making API calls, and the top two will be representing the two different users, user A, user B, collaborative on a document. Everything you are about to see is running live in a local Kubernetes cluster. First, I will register and log in our two users. With our user authenticated, user A now create a new document. And now user A will share this document with user B. The step is complete. Now let's connect both users to the real-time session. As you can see, both users have connected successfully via WebSockets. Now watch as user A types hello, and the operation is instantly received by user B. Now user B will add word world, and user A receives it. The collaboration is happening in real time. Finally, user B will undo their change. And like that, server inverts the last actions and sends a delete operation to both clients, keeping them perfectly in sync. So how does all of that work? Let's look at the architecture diagram on the left. The entire system is designed as cloud-native microservice architecture, specifically to address the assignment's requirement. The requirement for scalability and high availability is met by orchestrating everything with Kubernetes. Each of these boxes, user service, document service, and etc., is separated container deployment. This means we can scale each service independently based on load. For high availability, Kubernetes provides self-healing. If any service pod crashes, it's automatically restarted. For the security requirement, all users' requests first hit Kubernetes ingress control, which act as our secure API gateway. The user service issued industry standard JWT's authentication, and every API call and WebSocket is protected by an authorization middleware that validates these tokens. The demo you just saw involved multiple services. When user A and B connected via WebSocket, the ingress routed them to the real-time service. This service handles the live session. Now let's look at the requirement for database choices. We have used a polyglot persistent approach. For structured data like users and permissions, the user and document services use PostgreSQL, a reliable relational database. But for the high-speed needs of the live editing sessions and undo stack, the real-time service uses Redis and in-memory cache, ensuring low latency. This brings us to communication methods. When a user connects, the real-time service needs to know if they have permission. It does this by making synchronized REST API call to document service. The user has to wait for this immediate check. But the system also uses asynchronous communication. Let me show you. This is the management UI for RabbitMQ, our message broker. And here are the live logs for our notification service. Watch what happens when I rerun the command to share a document. The command returned success instantly. Now look here. Received a message log appeared immediately. The document service didn't wait. It just published an event to RabbitMQ, and the notification service picked it up asynchronously. This decouples our service and makes the system more resilient. A key part of maintaining a microservice system as required by deployment and DevOps criteria is observability. We have deployed a full observability stack. This is Grafana. First, let's look at centralized logging. All logs from all pods are collected by Loki. As you can see, I make a login request. The log from the user service appeared here instantly. We can debug any service from this single dashboard. Next is metrics and monitoring with Prometheus. Prometheus scrapes metrics from all services, allowing us to monitor their health in real time. We can track request rates, error percentages, and resource usages to ensure the system is healthy and to know when we need to scale. In a summary, this project is a fully functional cloud-native collaborative editor that meets all the core requirements of the assignment. It is scalable and high available thanks to its Kubernetes-based microservice design. It uses synchronous and asynchronous communication methods appropriately. It is secured with JWTs and central gateway. It uses a mix of PostgreSQL, and ready to meet different data requirements. And its maintainability with deployment tools like Kubernetes and Helm and is fully observable with centralized logging and monitoring stack. A key change was debugging the network with Kubernetes, which provide a valuable lesson in real-time, real-world troubleshooting. The architecture is highly extensible. Adding a new feature like email notification was done without modifying any existing core services, providing the maintainability of the design. Thank you.